Welcome to our presentation on very high cycle fatigue under biaxial loading of a mold tool steel. Now we're going to begin by introducing ultrasonic fatigue machines before we introduce our tension torsion ultrasonic machine solution and its basic concept. We're then going to talk about the specimen, the special specimens used here, the first design and the new improved design and the differences between the two, final element analysis, the tested material, the results of the experimental measurements and tests, and finally the fatigue results. Now the technology behind ultrasonic fatigue testing machines. These machines use resonance as a way to induce high-frequency fatigue. This is to study very high cycle fatigue regime between 10 to the power 6 to 10 to the power 9 cycles. If we compare this to the standard fatigue methods, to reach 10 to the power 9 cycles can easily take more than 1 month. While in ultrasonic fatigue machines, we can easily take less than a week. So this study started by observing a problem existing in ultrasonic fatigue testing machines that created this opportunity to be here, and what is the solution we are here presenting. If you look at the course of conventional fatigue testing method development, it began with a simple one-directional load tested methods. As research increased, it went towards multi-load testing methods. Now, ultrasonic methodologies want and will follow the same trend. They began with simple uniaxial tension compression, bending, pure torsion methods, and now they desire to go towards multi-axial methods. Now, here's the opportunity to create the methodology and the standard of multi-axial ultrasonic methods, mainly the most applied in conventional tension torsion and cruciform axial. So the first successful and reliable multi-axial method will be the standard followed by other researchers. So here we present our solution towards tension and torsion in ultrasonic fatigue methods. To our knowledge, is the only available multi-axial tension torsion ultrasonic fatigue machine available to date. We use as its base the uniaxial tension compression fatigue ultrasonic fatigue machine, the most used in research. We changed the horn and the specimen in order to include the torsion to the tension compression already excited. We have only one fatigue testing region in the specimen, and we also can adjust to a desired tension and torsion ratio. So the tension and torsion in this machine are in phase, and we can have a lower shear to tension, equally torsion to tension, and even a higher torsion to tension amplitude. So what enables the torsion simultaneously to the tension and compression is a special pattern horn we apply in our design. Here the horn transforms the actual displacement coming from the booster and the piezoelectric transducer towards a combination of rotation and actual displacement that is transmitted towards the specially designed specimen. Now, because the specimen receives the two types of displacements in phase, the rotational and actual displacement, the specimen needs to be specially designed to be able to enter in resonance in two different modes, one for the actual displacement and one for the rotation. For the actual displacement, the specimen is excited in this first longitudinal resonance mode, where it compresses and stretches, having only one region of high deformation, very similar to the tension compression in the actual ultrasonic fatigue specimen. Now, for rotation, the specimen needs to have 3 throats in order to have 20 kHz third rotational resonance mode. This creates 3 different high shear deformation regions, where the specimen in the cylindrical regions changes the direction between throats. When it's excited in the two presented modes, the first longitudinal and the third rotational, the result, the deformation result is here presented on the bottom, with one single high deformation region, the fatigue testing region. Here we can see the modes separately. The first longitudinal mode, stretching and compressing, and the third rotational mode with the different rotations in the different cylindrical sections. Looking at the overall setup, we still have the axial booster, the multi-axial horn, and the multi-axial specimen. We divide the three throats into secondary throats and to the main throat, the fatigue testing region throat. And here we have the free base where we will conduct the displacement measurement just as the uniaxial tension compression fatigue specimen. Looking at the final element analysis, this was the tool that enabled the complex design of the horn and the specimen. Through changing the specimen in specific manners, we can achieve the desirable tension-torsion ratios. Only with a finite element analysis is this possible. The first tested specimen geometry took into account the rotation deformation distribution as a rule for the following dimensions, meaning when in the beginning as a quarter wave, meaning A, and then as a half wave, then 2A. This results in an even distribution of rotation deformation and therefore a low difference in shear between the secondary and the main throat, the fatigue testing region. Because of this, the difference between the secondary and the main throat's stress combination is not as considerable, and therefore we don't have as pronounced a fatigue testing region, something that is undesirable. The new specimen took this into consideration, and the solution also provided the ability to change the shear tension stress relation. Now, the improved multi-axial specimen here tested in this study was made simpler with only 4 main variables, A, B, C, and R. By changing the relationships between A, B, C, and R, we can apply different shear amplitudes between the secondary throats and the main throat. Here we can see the result for one specimen where we clearly have a higher shear amplitude in the main throat and therefore a much higher stress combination in the main throat fatigue testing region. And this ability allows us to change to the desirable torsion axial stress ratio. Now, using the basic mechanical properties of the mold steel ACP20 here applied in this study, we designed 3 different multi-axial specimens. Now, looking at the experimental results, we first conduct a thermal analysis to all created specimens. Because in ultrasonic fatigue machines, high strain rates are applied, a high heat generation occurs in high deformation regions. So, by having a high heat generation at the main throat, we prove that we have a higher stress combination in the main throat, the fatigue testing region. So we made displacement and deformation measurements. To the displacement measurements, we applied 2 different vibrometer lasers to the specimen, one associated to the actual displacement, just as tension compression in the actual specimen, and the rotation is applied to small machine grooves at the free base of the specimen. To measure the formation, we applied a rosette strain gauge in the fatigue testing region, the main throat. Displacement and strain measurements were both conducted in axial and multi-axial horns. We can clearly see that the axial displacement and axial stress have a linear relationship between all horns and in all specimens. Now, looking at the shear stress, they still have a linear relationship, but they present a different amplitude between different and same geometry specimens. Now, when conducting fatigue testing to the multi-axial specimens, the results and the way we handle the specimens is equal to the uniaxial specimens. We applied high deformation, and when the specimen creates high enough fatigue crack propagation, the specimen loses resonance, the test comes to a halt, and the specimens are fractured in another machine. With access to the fatigue fracture surface, we can compare now the fatigue fractures between different stress, shear and actual ratios. We can see that lower shear in relation to the actual presents a very similar to tension, compression, fatigue, fracture surface tested specimens, where as we increase the shear in relation to the actual, we start to observe torsion fatigue marks, as we see, for example, for 0.5, and when we increase to a higher amplitude shear in relation to the actual, you can clearly see this high shear damage applied to the specimen. Looking at the same specimen with higher shear to amplitude stress ratio, we can observe the staircase fracture shape associated with the torsion damage applied to the specimen. Another parameter differentiating different ratio specimens is the crack initiation angle, when we can observe a direct increase in the angle as we increase the shear and actual ratio. In conclusion, all tested specimens with the improved geometry have proven reliable, guaranteeing the highest stress amplitude in the main throat, the fatigue testing region, the highest heat generation location. Shear has proven in amplitude variable between specimens, but still with a linear behavior. With continuous improvement of multi-axial horn and multi-axial specimen design, we will reduce shear amplitude as the continuous work of this study has proven. All fatigue fracture specimens presented a surface initiation, and comparing all specimens with different shear actual ratios, we can clearly see differences between shear damage and actual damage, and in angle of crack initiation as well. On behalf of our team, we would like to thank you for all your attention.